In this video, we're going to be talking about whether a system of equations, linear equations, has a solution at all. In other words, whether a solution exists. And we're also going to be talking then about if such a solution exists, is it the only one? Is it unique? Or are there potentially more than one? Now, I'll start by reminding us that a system of linear equations can either have no solutions, one solution, or an infinite number of solutions. Right? A system that contains a line and a parabola, for example, might have two solutions. But because lines are straight, a system of linear equations can only have no solutions, one solution, or an infinite number of solutions. So our first question here then is, does a solution exist? Right? A solution will either exist or it will not. If a solution exists, there's either one or infinitely many. So let's take a look at how we can figure out whether a solution exists. We know a solution exists in this matrix for this system of equations because this is the one we just did in the previous video. The solution that exists had to be written in parametric form, however, because there were an infinite number of solutions. And there are an infinite number of solutions because we had a non-pivot column in the matrix. If I take, because this is a system in three variables, if I insist that it have 3 rows, then my third row would necessarily be all zeros. And that doesn't really add anything to the matrix, so we usually just leave that row out. It doesn't tell us anything about the third variable that the first version of this matrix, this one right here, already tells us. So that extra row of zeros is really unnecessary. But seeing it there or visualizing it there can help us understand that this is a system with an infinite number of solutions, right? If you take this last row here and write it in equation form, then you have 0x1 plus 0x2 plus 0x3 equals 0. Well, that's always true. This is like saying 0 equals 0, right? So since that's always true, it doesn't matter what your input is, it's always going to produce an output. So that means we have an infinite number of solutions. And we said that that was going to be the case when we had a pivot column for each of the two variables. In this particular example, x1 and x2 were basic variables, but x3 was a free variable because this is not a pivot column, right? So in this example, which is the same one as we did in the previous video, we can see not only that there is a solution, but that there are infinitely many solutions, simply by looking at the form the matrix is in. Let's take a look at what happens if we modify this second matrix just a little bit. This is going to render it a different matrix, right? This is no longer the same system of equations. It's very similar, but it's not identical. I do this. My first row is the same. My second row is the same. My third row, instead of being all zeros, has any number here. I'm going to put a 9 there. What the heck? Okay, so for this matrix, I now have, again, if I transform this back into equation form, I get 0x1 plus 0x2 plus 0x3 equals 9. And that's like saying 0 equals 9. Well, that's never true, right? So the system of equations that leads to this matrix has no solution. And I can tell that also just by looking at the matrix because of this last row here, right? Everything to the left of the artificial bar there represents a variable or a number of a count of how many of each of the variables we have. And if those all add up to 0, and yet there's a non-zero number here, well, then it's never going to have a solution. It's not going to be a solution to the system. It is never true that 0 equals 9, no matter what values you choose to use for the variables. So this system has no solutions. On the other hand, this system has an infinite number of solutions with the one change in, let's see, I'll use a different color here. With the one change in the number in this position here, we have a completely different scenario. In the first case, we have an infinite number of solutions. In the second case, we have no solutions. Where there are an infinite number of solutions, we can tell by noticing that there's a non-pivot column in the matrix. That tells us that there's a free variable, and when there's a free variable, there are infinite solutions. In the case where there is, this is technically a pivot column. If I rewrote this matrix without the bar, I would have 1, 2, -1, 4, 0, 1, -2, 8, 0, 0, 0, 9. And this last column here, this is a pivot column because the 9 is a pivot, right? That 9 is a pivot. So when I have a pivot column in the last position, the last column is a pivot column, then there are no solutions. Let me provide one more matrix here for us to play with. I'm going to erase this version of this one. And again, I've made just one minor change here. I've changed the number in that position to be a 1 instead of a 0. I could also have returned this number here to being a 0. It doesn't really matter what's in that last column. What's critical is that I've changed the third column to be a pivot column by putting a pivot in that position there. Now that I've done that, I can look at this system and say, well, x sub 3 equals 0, or x sub 3 equals 9, depending on what's in this position. X sub 3 equals 0, and if I know x sub 3, then I can substitute back into here. I know what the numerical value is for x sub 3, and then I have 1 x sub 2 minus 2 times, in this case it's going to be 0, equals 8, and I can back substitute in to figure out what x sub 2 is, and then I can back substitute x sub 2 and x sub 3 to figure out what x sub 1 is. That's not necessarily how we're going to do all of this when we get to the actual solutions, to the solving of matrices. But by way of explanation, the fact that I can do that means that I can look at this, notice the things that are in the various positions in the matrix, and I can say that if the last column does not contain a pivot, then there's going to be one solution to this system of linear equations. One thing that I'd like to point out here, this is really quite important, is that these are all in echelon form. In fact, these all happen to be in reduced echelon form. That's not strictly speaking necessary. It's not necessary for them to be in reduced echelon form, but they can be. As long as they're in echelon form, you can make these observations, right? You can tell by looking, once it's in echelon form, you can tell by looking at a matrix. First of all, whether it's going to have any solutions, and if it does have solutions, whether there's going to be one solution or an infinite number of solutions. We have a theorem in this particular case, so I'm going to go to a different screen and write out the theorem, and we'll talk through it. We've pretty much covered everything in the theorem, but I want to look at the more formal language and help kind of break it down and interpret it a little bit. All right, this theorem actually has two parts, but I'm just going to do one part at a time. This one says a system of linear equations is consistent if and only if the last column of the augmented matrix in echelon form or reduced echelon form is not a pivot column. So let's take a look at a couple of key phrases here. The first one is this: if and only if. The phrase if and only if has a very specific meaning in mathematics. If I say, I will get wet if it is raining, and actually I could turn that around and say, if it is raining, then I will get wet. That implies that if the condition that it is raining is met, then the fact is that I will get wet. The other direction doesn't necessarily apply there. If I get wet, then it is raining. Right? If I get wet, it might have just taken a shower, or a car could have gone by and splashed me, or I jumped in the lake. There are a lot of different ways I could have gotten wet. So to say, if I get wet, then it must be raining isn't necessarily true. So I can make a statement in one direction and not the other, necessarily. On the other hand, if I say something like, if the sun is out, the sky is blue, I can turn that around and say, if the sky is blue, then the sun is out. In that case, it's true in both directions. And that's where this phrase if and only if comes in. Instead of saying if the sun is out, then the sky is blue, and if the sky is blue, then the sun is out, I can simply say the sky is blue if and only if the sun is out. And in mathematics, that implies both directions work. There are a couple of different symbols we sometimes use for that. Let's say the sky is blue is B, and the sun is out is S. I can either say BIFF S, that means the sky is blue, if and only if the sun is out. And sometimes you'll see B with a double-headed arrow, and then S, B if and only if, B if and only if. This is a bidirectional conditionality. You're not going to get tested on all of that in this class. I want to make the point that this expression has a very, very specific meaning, and it's important to notice that what it's doing is connecting these two other expressions in a way that is kind of unique in a way. So I'm going to take a look at what those two expressions are. The first one is this: a system of linear equations is consistent. So that is a condition that can or may not be met. And the other one is this long one here, that's the last column of a an augmented matrix in echelon or reduced echelon form is not a pivot column. So there are two different things here. One is the system of linear equations being consistent, and the other is that the last column of an augmented matrix in echelon form is not a pivot column. So we have the last column is not a pivot column. That's one statement. Another statement is a system of linear equations is consistent. Now this theorem says that it doesn't matter which one of those things you start with. If you have one, you automatically have the other. If a system of linear equations is consistent, then the last column will be a non-pivot column. Equally, if you have a matrix in echelon form where the last column is not a pivot column, then the system will be consistent. It works in both directions. That's the beauty of that if and only if statement. Otherwise, I'd have to write this whole thing out twice. Okay, so what is this really telling us? A system of linear equations is consistent means it has a solution. Now, at this point, we don't know whether it has one solution or an infinite number of solutions, but it does have a solution. And that can only be the case if in echelon form, the last column of a matrix is a non-pivot column. Okay, so if you're looking at a matrix and it's in echelon form, it has to be in echelon form. If you're looking at a matrix and its last column is not a pivot column, you know you've got a solution. You don't know whether you've got one or an infinite number, but you at least know that there's a solution. Otherwise, the system is inconsistent. So if you have a solution, then you know you have a non-pivot column in the last column. Or if you have a non-pivot column in the last column, you know you have at least one solution. If you don't have one or the other of those, you don't have both. And if that's the case, the system is inconsistent. That's all that last sentence means. Either the system is consistent or it's inconsistent. If it's consistent, the last column is a non-pivot column. Okay, so now that we've decided, or now that we've sort of determined how to tell whether a system is consistent or inconsistent, right? Basically it has a non-pivot column in the last column. If it's consistent. If it's inconsistent, it doesn't. If it's consistent, it could either have one solution or an infinite number of solutions, and that's what this statement says. In the following statement, we're going to talk about how to determine which is which. So This statement here is just saying if a system is consistent, if the first condition is met, the system is consistent, then either it's going to have a unique solution, one solution, or infinitely many solutions. All right, we got to here. The following sentence, the solution to a consistent system is unique if and only if the system does not contain a free variable. This is another use of that. Let's highlight the phrases that occur either side of that expression, that phrase. Okay, the solution to a consistent system, right, one that has a solution, that solution is unique if and only if the system does not contain a free variable. Because of the if and only if statements, I can read this two different ways. The solution to a system is unique as long as the system does not contain a free variable. If the system does not contain a free variable. Equally, though, I can say because of the if and only if statement, the system does not contain a free variable if the solution to the system is unique, right? So I can go in either direction again here. It's really quite a powerful statement to be able to make. It might be interesting to note that this if is only an if. It's not an if and only if, right? So if a system has infinitely many solutions, that doesn't necessarily mean it's consistent. What this if is saying here is that the system has to be consistent in order for there to be either one or infinite solutions. If there is either one or infinite solutions, that does not necessarily imply that the system is consistent. So that's the difference between just an if and an if or only if. So we've established that a solution is unique if and only if the system does not contain a free variable, but equivalently, a consistent system has infinitely many solutions if and only if the system contains at least one free variable. So if the system contains at least one free variable, if you can find a free variable, there are infinitely many solutions. And if you already know that there are infinitely many solutions, then you know you're going to have at least one free variable. So how do we want to use this? We've really kind of already discussed all of this. This is a more theoretical sort of look at it, a more formal look at the situation. But basically, if you look at a matrix and there is at least one free variable, then you know you have infinitely many solutions. One free variable, infinite solutions. Okay, that's this one right here. No free variables, then the solution is unique. But notice that these both came from the second statement here. And the second statement says, if a system is consistent, right? So I also know that these are for a consistent system. And how do I know it's consistent? I go back up to this statement up here. It's consistent as long as the last column is not a pivot column. No last pivot column. That's pretty ham-handed, but there you go. So that's that situation. If you do have a last pivot column, then that first condition is not met and you have an inconsistent system, which means you have no solutions. So the first thing I would look for would be a pivot column. If you don't have one, then your system is consistent and you go to step 2. If you do have one, you have no solutions. So identify a pivot column, you know you have no solutions. No pivot column, then you look for a free variable. And that's pretty much what we did in the previous slide, right? Earlier in this same video, but this formalizes a little bit. This is the theorem in our textbook that's called 1.5.1 Existence and Uniqueness Theorem. Other textbooks would definitely have a different label on it, right? They wouldn't call it theorem 1.5.1. They might call it the existence and uniqueness theorem. In particular, it's important to note that it's the existence and uniqueness theorem for solutions to linear systems of linear equations.